Hello students, welcome you all for physics session. Well, dear students, in the last class we have started already the second chapter of second PUC, that is electric potential and capacitance. Well, the potential concept is quite very interesting phenomenon in electrostatics. Though we have studied the first chapter about electrostatics, about electric charge. Now we are at the stage to describe the charge phenomena, the charge causes, the charge effects, such as the interactive force, at the same time electric potential. Electric potential, we have defined the electric potential, we have defined the potential energy also, we have defined the just potential at various cases in first PUC physics. Though in today's chapter or in today's session we are going to discussing about the few formulas which are related with electric potential. Okay, now in that case, first one we will discuss about the electrostatic energy of two charge system. First of all, I want to clear one point clearly, is that about the potential concept. Let us say we have a three-dimensional picture over here. We have a x-axis, y-axis and z-axis, where we have the origin O at this point. Let us say we have a charge Q1 here. Okay, now and we want to we'll go for the point, just I will take a reference point, I will take it as A. Reference point is A now, and from origin it has some distance R or X, you may take it. Okay, now so I want to bring some charge of let us say we have a magnitude of Q. And first of all, the point is very clear that the charge Q we don't know very exactly. Okay, so for reference point we take the infinite distance. Yes, it is true that we may bring charge from infinite distance also or for finite distances also. So at this case, if suppose I want to bring this charge Q from wherever, it may be at infinity. If suppose I want to bring this charge to my reference point, that is A, where I clearly know about this point. Where the exact coordinates are there, space coordinates are there, Cartesian coordinates are there. I know very well about this point, but I do not know about where exactly charge is situated and how can one bring it to my reference point. And though the electric potential concept has started there. Okay, now so suppose I wanted to bring this charge from infinite to my reference point A, nothing but I must do work on it. And as in first year physics we have discussed or we have defined as the amount of work done in bringing the unit positive charge or some other object from infinite to my reference point. So that amount of work is nothing but we will say potential. And as you know, electric potential is defined as V. Okay, and the point existed is that electric potential is not only just simplified or restricted for a point charge only. Why? Because in any references area, we may go with the several such coordinate variables, several such coordinate areas, several infinite distances areas, surface areas. Okay, we have sphere, circle, square, rectangle, trapezoid, polygonal. We have such so many various areas. No? So depending on those all points, number of charges are going to reside, number of charges are going to distribute over the surface. So at that point, we can't describe or discriminate electric potential and potential energy for just only a point charge. So now we will go for electric potential energy or electrostatic energy for 2-point charge system. So formula will be, I want to clear one more point here only. These formulas are directly denoted in your syllabus. These derivations are not in your syllabus. Okay. Now, so move on to U is equal to, as you know, V letter indicating the just electric potential, whereas U indicating electric potential energy. Okay. Now, so electric potential energy U is equal to 1 divided by 4 pi epsilon naught Q1 Q2 divided by R. Okay, so here at this point I have just taken a point charge and a reference point. Now I may take it as, I may go in for two charges Q1 and Q2, such that A and B, these are the points where the charge Q1 and Q2 are located. Now if suppose I want to calculate or I want to measure the electrostatic energy between these two charges, I must deal with the distance between them. Okay? Now, because of that point, we need to discuss, we need to refer the distance R here. Now move on to, if suppose I want to take it for 3 charge system. So now the formula has to change the following method. U is equal to 1 divided by 4 by epsilon Q1 Q2 by R12. Because here I am discussing with charge Q1 and charge Q2. Later here I have considered the 3 charge system. Nothing but I have taken here Q3. And this charge Q3 is related with Q1. At the same time, this charge Q3 is related with Q2 also. At the same time, Q1 and Q2 are correlated very early. So, for such a system, I need to go for Q1, Q2 by R12 plus Q2, Q3 divided by R23. Nothing but the distance between Q2 and Q3. And later on, I must conclude, I must take Q1 and Q3 also, because these are also correlated with each other. So I must take R13 also. So in general, suppose I have a n number of charges, like I said, 10 charges, 20 charges, 100 charges, to make n charges. So in generally, I must take it as U is equal to 1 divided by 4 by epsilon naught summation. Where do we want, or where do we apply the summation? Where do we have a electric or general mathematical sum? Where we are including all the things, we will apply the summation. No. So here I have written the summation. Nothing but you have to take individual values togetherly by adding those values. Okay. Now summation of I is equal to 1 to I is equal to n. I is indicating the first charge, that is Q1, reference charge. We will take it as a source charge. Let us say source charge. So source charge, it may be start from I is equal to 1 to I is equal to n. Now Qy, it will be remain same now, so we will take outside and the variables will take it in bracket side. Okay, 1 divided by 2, the formula remains same only. The formula remains same only factors are going to change. Okay, so 1 divided by 2, summation of j is equal to 1 to j is equal to n. So you may take the second charge from 2, 3, 4, 5, 6, 7, 8, 9 up to n number of charges. At the same time, here one point is very important, where I is not is equal to j. This condition is not required now. If suppose you have the same number of charges, charges might be cancels. Okay, move on to Qj divided by Rij. Nothing but we have to discuss about the charge of the J concept. Few minutes back we have discussed the space coordinate system. At the same time, we defined about the Cartesian coordinate system. So these all points will give hint or will help us to describe the point surfaces. Okay, and move on. So this is what about electrostatic energy. And move on to, at this point we will discuss about electric potential energy in the presence of external electric field. Yes, it is true that these charges are going to affected by applying certain external electric field. Yes, it is true that here we have studied at the static motion. Nothing but there is no such electric field. But here we want to discuss, if suppose you apply the external electric field, yes, it is true that charge magnitude has to change. Why? Because according to Coulomb's law, we have said that magnitude of charges are going to change in accordance with the magnitude of other charges, right? Now move on to, in that case, first of all I will discuss for single charge, and then I will move for the 2 charge system, 3 charge system, and later we will go for the n number of charge system. Okay, now move on. The first point we discuss about the, for a single charge. If suppose in a space we have a only single charge of magnitude q. Okay, so for a single charge, what could be the electropotential energy in the presence of external field? As we know that amount of work done is equal to energy U. Okay, and move on to just to define the electric potential energy. What do you mean by electric potential energy? It is the amount of work done in bringing the unit positive charge, right? So I want to recall here, potential V is equal to W divided by Q. This is the basic formula we know already. What do you mean by V? Electric potential. What do you mean by W? Work done. What do you mean by charge? Q, right? So W is equal to U is equal to Q into V. Simply W is equal to Q into V. We'll have the electric potential energy in presence of electric field. And move on to second point. Two charge system. U is equal to Q1 of V of R1. Okay, the same thing. Q into V. Here we have only one charge. Well, we'll just put it as Q into V. But here the case is different. We have two charges here. Q2 and Q1. Okay. Now, this is also having some distance R1 and this is also having distance some R2. At the same time, these two charges are separated by some distance R1. So at that point, I must require Q1 into V of R1 plus Q2 into V of R2 plus the same thing 1 by 4 pi epsilon naught as we taken here Q1 Q2 by R12. Nothing but I must take individual displacement vectors or displacement point and later I must go with the reference point. And later the third, the three charge system Q of VR1 plus Q2 into V of R2 plus Q3 into V of R3 plus the whole factor. So these are the formulas one must note to discuss electric potential energy. Okay, now move on to in continuation with the point electric potential energy of a electric dipole in uniform external field. Well, students, in few minutes back we discussed about the electrostatic potential energy for a single charge, two charge system, three charge system in external electric field, but we have just taken the expressions. Okay, now but we do the derivation for electric dipole. What exactly happens for an electric dipole when that electric dipole placed in a uniform external field? Okay, now so for this derivation we must require the definition of electrostatic force, electrostatic field or electric field, and electric field strength. Okay, now move on. Let us say we have an electric dipole where it is placed in a uniform electric field, external electric field. So these lines what I have indicated with arrow marks, these are representing the uniformity. Okay, now move on. If suppose I place, let us say consider this chalk piece is an electric dipole. Okay, so we have the unlike charges over it at the end of the conductor or electric dipole. If I place this electric dipole in such external electric field, external field is going to act on it and it will disturb the uniformity of this electric dipole. And how exactly it is going to defect or affect the electric dipole? Okay, now in this session we are going to be discussing about this fact. Now move on. If suppose I place it this, anyhow it's a electric dipole, torque must apply. No? Yes, because of the action of the external electric field, it has to experience a force, and that force is nothing but torque, the rotational force. And because of that fact, it may take the rotation. Whatever the diagram of things are shown here, this is the representation of the electric dipole. Okay, now so it will be of plus Q charge and this will be of minus Q charge, separated by some small distance, let us say 2a. Okay, so this will be the center. As this electric dipole is under external field, it is losing its capacity to be in a static way and it gets started to rotate it in this direction. And continuously rotation affects the change in this angle, and I will call this angle as small angle, that is d theta. And due to the variation at this angle, particular angle, the torque has to be changed. And because of this change in torque, electric dipole moment has to change. Why? Because we have defined the electric dipole moment as it is a product of either charge and the distance separated between the electric dipole. Correct? And move on to, as the angle is changing, torque has to change. And torque is changing. It is indicating what? It is indicating that this electric dipole is affected by the external electric field, where it exactly not happens in the previous case where we have taken in the absence of the external electric field. And though we'll say that yes, torque is applied for electric dipole, or other way we can say it as electric dipole is affected by or is under the action of external electric field. And because of that, it is moving, nothing but changing the angle, and work has to change. No? Work is done, right? You are applying external force on it, nothing but you have applied the electric field over here. And we can define electric field as it is the amount of force. Yes? So force applying in rotational way. And this amount of torque is acting on an electric dipole, indicating that you are doing some amount of work. No? What do you mean by amount of work done? Work done is equal to potential energy. And though we will define electric potential energy in dipole in uniform external field. Okay? And move on to related to this point, as we can define the torque tau is equal to P cross E. First of all, I want to write this in a vector form. Electric torque, electric dipole moment, and electric field. Tau is equal to P cross E. These formula, these derivation we did in first chapter already. Okay, we move on to tau is equal to PE sin. Right? Move on. So as the theta going to change, sin angle will change. Though it's in product form, so sin theta changes, nothing but torque is changing. Okay, now tau is equal to P. So here at this point we came up to the point of tau is equal to PE sin theta. I will repeat once again the point. Tau is a rotational force. P electric dipole moment. E will be external electric field. And now in the previous chapter we have defined tau is equal to P cross E, that is tau is equal to PE sin theta. Now, so you are calculating what exactly here? We are just calculating the electric potential energy, right? And you already know the definition of electric potential energy. Now, what do you mean by electric potential energy? It is the amount of work done, correct? Huh? So at that point, I must calculate first of all work done. Right? And you already know the definition of work done. W is equal to F into ds, where we are applying the linear forces there. But here the things are different, no? Here we are applying the rotational force. Why? Because force is continuously acting with respect to d theta. Here we have angular displacement instead of linear displacement. Okay. So for that I must require what is the smallest amount of work done. Later, I will go for total work done. Okay, na? So dW is equal to tau into d theta, as we discussed in linear force. W is equal to F into ds. But here we have dW is equal to tau into d theta. So W is equal to integration of dW. If we know the small amount of work done, it is very easy to calculate or to measure the total work done. So W is equal to what you are supposed to do? Just to integrate the things now, what do I get from differentiation? So W is equal to integration of dW Q1 to Q2. And move on to, what do you mean by dW? dW is nothing but force, torque. So torque is nothing but PE sin theta. So integration of PE sin theta into theta. Okay. Now just we integrate the PE sin theta. Electric dipole moment constant. Uniform external field is there, it is also constant. So what left hand here? Left hand thing is Q1 to Q2 sin theta into d. So PE, what do you mean by integration of sin theta? Integration of sin theta is minus cos theta. So but what is the left hand thing here? We don't know exactly where it started to rotate and where it is exactly going to end. I am talking about the angular displacement, man. Here I have a charge plus q, theta 1. Here I have a charge minus q, theta 2. Okay. So for every action, there will be initial angle and to the final angle. See, this electric dipole initially is in the direction of external electric field initially, very earlier. When I started to apply the uniform external field, it gets started to rotate. Nothing but it is continuously losing its uniformity. Okay, now, so at that point, what happens here? Initially, it is at the angle Q1. This will be the angle theta 1. And later it gets started to rotate by the action of external field, and somewhere at some instant it stops when you stops the external electric field. So that point will have the theta 2. Okay, now so these are thetas, not q. Keep in mind theta. Okay, now angles. Now we don't know exactly the theta 1 and theta 2. Okay, now move on to PE minus cos theta of Q1 or to the Q2. So theta 1 to theta 2. So these are the variable angles. Now apply the upper range and lower range. PE minus cos, in the place of theta, first of all substitute theta 2. In the place of theta, substitute theta 1. Here already have a minus. Minus into minus it will be plus. So cos theta 1. Okay, now move on to what exactly the formula we have now. PE bracket minus cos theta 2 plus cos theta 1. Start. Okay, now we have the formula right over here. W is equal to PE into bracket minus cos theta 2 minus cos theta 1. If now we can take the condition, several cases. If theta 1 is equal to pi by 2. If theta 2 is equal to 0. Okay, now so at that such condition, what exactly the amount of work done will be? So W is equal to PE, I'll take the sign as it is, minus cos theta 2. What do you mean by theta 2? Theta 2 is 0. Plus cos theta 1. What do you mean by theta 1? Theta 1 is pi by 2. That is nothing but 90 degree. So as we know, cos 0 is maximum value, no? What do you mean by cos 90? 0. So what happened here? W is equal to minus PE cos 0 is 1. So I will take it as theta, or simply I will take it as cos theta. Minus is there, no? So I will take minus PE cos theta. What do you mean by cos 90? Cos 90 is 0. 0 into 0 will be 0. So the thing left is W is equal to minus PE cos theta.